Okay, fine. So let me go ahead with the initial stage things. So what we have to talk is about the materials. There are wide range of the materials having the melting point from say less than 100 to say more than 2000. Likewise, the materials having the very low yield strength of 100 MPa to say 1500 MPa or even 1800 MPa yield strength. Likewise, the hardness, very low hardness, 5 HRC to say 65 HRC. So the properties of the metals vary or the change significantly. So what are the material properties that are important, especially the metal properties that are important in the manufacturing? So from the mechanical properties point of view, there are three broad categories which are important. In mechanical properties, there is yield strength and the percentage elongation, which is called ductility. Okay. So these two are particularly important in machining and forming. Metal must be able to deform, must be able to get sheared off. Likewise, the hardness. So these are the three main mechanical properties that affect the manufacturing related selection of the processes. Also, it will be making the processing easy or difficult. So I don't think I need to explain all the properties, like the stress level at which the deformation starts, that's the yield strength, and the elongation is the kind of the strain that can be induced prior to the fracture, and resistance to the hardness or indentation. Whenever a pointed object acts onto any surface, then it indents or tries to penetrate. So that is what defines the hardness. Okay, so it is simply resistance to a scratch, resistance to indentation, etc. Physical properties which matters in manufacturing includes like the melting point temperature, low melting point temperature or high melting point temperature. This is important particularly for the manufacturing processes like casting and the welding, where fusion is involved. You need to fuse the metal, you need to fuse the parent materials which are to be joined. Coupled with this, also you have thermal expansion coefficient alpha and thermal conductivity. These will be determining how much expansion or contraction will be taking place when the heat is applied during the manufacturing. For forming, when the metal is heated to facilitate the deformation, or when metal is heated to fuse in the fusion welding processes, or when the shrinkage is taking place during the solidification of casting after the completion of the solid state, and how fast heat will be getting transferred, that will be determined by the thermal conductivity. So it will be indicating how fast melting will be taking place or how fast solidification will be taking place. That will be affected by your the thermal conductivity. Other properties like the electrical and thermal, it is magnetic property, electrical and magnetic properties. So those are other properties which also affect the manufacturing related aspects. I'll give simple example like in resistance heating. If in welding kind of process where current is allowed to flow, and if the resistance is low at the interface, you need very high current to facilitate the welding, and if the resistance is high, you need the lesser current value to facilitate the joining. Similarly, there are advanced manufacturing processes where magnetic properties will be important, and as far as the chemical properties are concerned, you need to see that what our material is being processed, it is not harmful for the human being. The metals like metal fumes, especially like of chromium and the lead, these are considered to be harmful. So nowadays lead free shoulders are being developed because the lead fumes are harmful for the human being and health of the human being. So the toxicity is the one thing. Stainless steel welding frequently creates stainless steel casting also creates problem because these fumes and the vapors of the chromium that adversely affects the health of a human being. It also dictates the corrosion related thing or the chemical action. So there is an advanced manufacturing process which is called electrochemical machining. So there the chemical activity of the metals with the with the chemicals will be playing some kind of the role. So these are the properties which need some kind of attention while choosing the suitable manufacturing process. Another important aspect as far as the manufacturing process choice is concerned is about the volume. Like how many units we want to produce, just 2 per day or 2000 or 20,000. So that significantly affects the choice of process. Every process doesn't have the same capability to manufacture at the same rate. Each process is unique. Okay, so depending upon the production requirement, what I will say, production requirement, rate of production that is needed, we have to choose the suitable manufacturing process. Like all manual manufacturing processes where manual intervention is needed, you cannot really achieve extremely high rate, because eventually the human being will be working on the machines or using some tool to make something, and you may not be able to realize very high production rate. So for low production volumes, job shops, batch production, maybe the manual manufacturing will be fine. But if you want very high volume production, like 20,000 units per day, then certainly you need some kind of the automation in the manufacturing approach. In manufacturing process. So all manufacturing processes cannot be automated. So those which can be, certainly they will be preferred over those which cannot be automated. So the volume of the production, apart from the material, the volume of the production also affects in a big way that is needed as far as the choice of the suitable manufacturing process is concerned. Just for an example, like say for batch production or for low volume production, flexible manufacturing process, value manufacturing systems, or regenerative processes can be used. Yesterday I talked about these regenerative processes. Though, and apart from this is also in addition to those manufacturing manual intervention based manufacturing process. If you want high volume production, then certainly we need to go for the automation or the heavy, big, robust automated machines. As far as the process wise is concerned, machining is good enough, like material removal based processes are good enough to realize the desired products, say maximum up to say up to 500 units. It's like per day, depending upon the production capacity. Again, there it's a very kind of subjective kind of thing, which kind of the facility, which kind of the machine that you have. And if you want very further higher volume of production, then deformation based processes are used when the number of units desired is more than 10,000 or so. It will depend, like nuts and bolts in 1 hour maybe you can produce 1,000. So depending upon the kind of product, depending upon the system that you have, that will be affecting the volume production rate significantly. But if we need low production, manual manufacturing processes or the FMS or regenerative processes will be fine. But if you need high volume production, you need to go for the deformation based processes, you need to go for the automation. Okay, so this is about your these are the two aspects. Then there are other quality related aspects. What are those quality related aspects? If you see, there are two aspects: how accurately we are able to manufacture the product again and again. Okay, so there are two words. One is called tolerance, like how repeatedly we are able to make the product of particular dimension. Say this is its length of, say we want it of length 10 mm, right? But it never always be 10. It may be like say 9.98 or it may be 10.2. So there will always be, so or there can be a variation in this range. So if that is happening, then what we can write, 10 plus minus 0.02. Okay, say 0.98, it will be 0.8. So 9.8 and 10.2, it will be like this. So in that case, the plus minus 0.2 will be the kind of variation both the sides about the 10. Our intention is to make it 10, but it will always be varying, not exactly always be hitting the target of 10 mm, but in actual manufacturing it will always be changing. It may be 9.98, sorry, or it may be 10.02, like this. So in that case, the variation about the mean value will be like this. So it can be, say, 10 point plus minus 2, or it can be 10 point plus minus 0.02. So this is very close variation is extremely small, and here the variation is very large. In this case the variation is very large, so we call it as a close tolerance or very loose or very high tolerance. So you need a very good control over the process, and extremely good manufacturing things will be needed to have very small variation in the dimensions when the product is being manufactured. So it is more difficult to have the 0.02 kind of variation as compared to the case when the variation is of 0.2. Okay, so this is like controlling the tolerance is controlled very properly, and good dimensional control is available in this case when the variation is 10 plus minus 0.02 as compared to the another case. This is the one aspect. Then the another aspect related with the manufacturing is the roughness. See, you see all the surfaces that you see around you, they will look like this, the flat, okay, but when you see at a high magnification, at a micro level, there will always be variation of this kind. Okay, the variation in magnitude may be small or it may be large. Okay, so this variation in which is there at the surface in form of these peaks and valleys, this variation is always there, and this variation has to be quantified. So with respect to the center line, what is the average value of height and depth? That is what is quantified in RA. So in one case it may be like, say, the this RA value may be, say, 5 micrometer in this case, and in another case it may be 50 micrometer. So you see what is the difference in the two. In one case the surface is having the very high peak and the deeper valleys. In another case the surface is having the narrow means shallow valleys and the peaks of the lesser height. So the surface roughness in this case is low. Okay, that we mention most of the time in terms of RA parameter, which may be, say, here in this case 2 or 5 micrometer, right? In another case the surface roughness is extremely high, just like you move the finger over the surface and you can see that it is unevenness is there and it is not really smooth. So this may be of the order of, say, 50 micrometer or even 100 micrometer. So depending upon the process being used, each manufacturing process has a capability to make the products of the different roughnesses. You see, so the roughness and smoothness, these are the two opposite words. So high roughness means means the smoothness is less. High smoothness means roughness is high smoothness means roughness is low. Okay, so this is an indicator of the high roughness, and this is as compared to that, this is smoother, the second one, where the RA value is changing in the range of 2 to 5 micrometer. Okay, so if we see the processes like casting process may offer you the roughness in certain category, like die casting. Maybe it can offer you 5 micrometer RA value. Its roughness surface is smooth. But if you use the sand mold casting, the roughness may be as high as that of the 50 micrometer also. So all processes do not offer the same level of hardness. Similarly, the deformation based processes, if you go for hot deformation, maybe it is 20 or 40 micrometer, but if for cold deformation based processes, maybe 5 micrometer itself. That will again depend upon the number of other factors, but each process has a different capability to make the products of the different roughnesses. Okay, so the roughness is another important thing that has to be considered, that will be affecting the functioning and the performance of the products which are being made. Okay, so now I'll show you some of the slides. Okay, let me show if I can switch over to this. Okay, so you can see this image. Okay, so this is the plot, just to have idea of Professor Varun, mute all the students because there is a noise, some kind of disturbance is coming. Okay, yeah, so this is a plot which shows the relationship between the volume of production that is needed, say in the x-axis, very low volume, say 10 units, or okay, fine. Right. Professor Varun, please unmute me. Hello. Hello. Okay, just a minute. Let me see. Okay. Yeah, it's fine. I think I'm now audible, right? Okay, that's fine. Oh, okay, right. So here, okay, so this is what I was saying. The property, how the property and the volume of production are related in this one diagram. Okay, it's fine. I'm audible. I'm audible now. Okay, so this plot relates the volume of the production and the material property in terms of the temperature. So the low melting point materials like polymer, most of the plastics, middle melting point materials like intermediate melting point materials like metals and alloys, say up to 1000 or 1800. Then the ceramics. Okay, and the volume of the unit, say just 10 or up to 10,000. If the two are clubbed, see, for moderate volume up to say 100 and the moderate for a very wide range of the hardness, the machining is good. For intermediate melting point temperatures to the low temperature, okay. No, but they don't have any right. I don't know. That's why I cancelled all the rights. I don't know. Today only this is happening. Okay. Okay, no problem. Let's go ahead. This is the joining is for the intermediate to the low melting point metals, and the manufacturing volume production can vary from very low 10 to say 10,000, like it is used in cars as well. Primary forming process like casting and forming, these are used for the low melting point materials as well as the high volume production. And the deformation based processes primarily used for the high volume production and for the metals as well as low and the intermediate melting point. The point is here, in manufacturing, the volume and the metal to be processed, these two significantly dictate the choice of the suitable process. Okay, so that's what I said. Now coming to the tolerance. the different processes offer the different tolerance. Say for casting, the tolerance is in this range, all right, in mm. Okay, for that is about the casting. Then for machining, the tolerance is very close. So the primary shape is realized through casting having the greater tolerance, and the tolerance is reduced when we use machining. Its close tolerance is realized, and during the grinding it is further closer, you see. And in non-traditional machining process it is intermediate. So grinding, the minimum tolerance and the maximum tolerance or higher tolerance is there in case of the cast process. So the different processes offer you the different capabilities. That is the point of telling all this this slide. Okay, now as far as the roughness is concerned, you see the roughness. The roughness in the case of casting can range from say very low value 1 to 2 micrometer to the very poor, say 10, 12 to 25. Even it is in some cases 50 for the coarse sand mold. Then metal forming, it is low, right? Hot forming, it is high, you see, as I said. So the forming process, the roughness is different. For machining, the roughness realized is really low. For finishing, it is low, very good and excellent surface roughness, surface finish is realized. And for non-traditional machining, it may range, it may be even not as good as it is expected, but it is not even finer than what is realized in the machining or abrasive finishing process. Normally, the thermal processes like arc welding, flame cutting, or the plasma cutting, they offer poor because the melting is the idea. Here you melt and then you cut. So the roughness is really bad in case of the thermal processes. Okay, so this is what is there. 4 categories as far as the roughness, ability of the different processes to make the things of the different finishes is concerned. This chart is just to show, just to have idea of, because I will be going again back to the white board. What it shows, like if say this is the cost is one factor, production rate is another factor, quality is another factor, and ability to get change and manufacture different kind of things, that's the another factor. So if the 4 are the major factors which are in consideration, then out of these processes, 5 processes, which one is to be chosen? So each offers the different capability. Since each works on the different principles, so they offer the different capabilities. Okay, so this is just the point. Let me go back on to the selection approach. Okay, so I'll be using again the whiteboard. Okay, so here what I have with me is this the procedure for selection of manufacturing process. Okay, so the first step here is identify whatever is good for you. Just develop a list the parameters of relevance or importance for you. Whatever matters, you just note it down. Relevance for the manufacturing point of view, whatever is important, it is cost, flexibility, production rate, availability of machine, availability of material, labor, whatever is coming, just note it down. Then out of that list, so this is called establish the selection driver parameters. Selection driver parameters, this the first step. Then out of those selection driver parameters, what is important, what is most important for you, then select the criteria which you will be using, you would like to use. So out of those so many parameters, come out with few. Select the criteria for selection. First develop a list, then select few that are most important for you. Okay, then considering these parameters or criteria or technological aspects, identify the potential processes. Identify the potential processes which can be considered for selection. Okay, then these need to be evaluated. Evaluate the processes considering the criteria that you have chosen for selection. Okay, so the processes versus criteria, these processes need to be evaluated. So for this evaluation, usually the decision matrix is applied. Okay, and then you select the process which gets maximum score in the decision matrix. So these are like say 4-5 steps which are used. So as far as going ahead with this is concerned, so what we have to do is the first of all the first step, the process selection drivers, or you can say just establishing all the parameters that are important for you. I'll just read out what those parameters can be. It can be quantity of or the volume of the products that is to be produced. It can be cost of tooling or the machines or equipment that is there. It can be the production rate that is to be realized. It can be the skill of the labor which is required. It can be the level of supervision of the manufacturing process which is required. It can be the energy consumption. It can be the availability of the materials and their cost. The parameters or the driver selection driver parameters can be like capability of the machines to process the material in question, product dimensions and size that is to be finished, surface finish desired, the tolerance desired, the wastage which is to be controlled, the maintenance cost, and eventually all total costs. All that the parameters, this is simple list. All may not be important. Okay, so you need to see that establish among those many parameters, establish your own priority list of parameters. So which may be in form of say the volume or the production rate, which can be the cost of the product at which you want to make it. It can be the geometry of the part which is to be produced. It can be the tolerance that is to be realized for proper functioning, or it can be the metal which is to be processed. So all that is to be prioritized. As far as the selection of manufacturing process is concerned, the moment you talk like for a given product, these are the properties desired, and for those properties you have identified a particular metal. The moment you identify the metal, the choice of the processes is narrowed down significantly. Why? Because say if the material is polymer, you know that injection molding kind of the process or the plastic molding processes need to be used. If these are the metals of the low melting point, you know certain processes are there. If the material is of the very hard and it is made of ceramic, you know that the powder metallurgy or the advanced machining processes need to be used. So the moment you identify the metal or the material of which product is to be made, the process selection or the process choice is narrowed down significantly. Okay, so if it is low melting point, you can go for welding, you can go for casting, and there are a number of casting processes. Likewise, it is low yield strength and high elongation, you can choose the deformation. If thickness is less, use forming. If thickness is more, some other processes are to be used. Okay, so Then the volume of the production is the another important parameter. Like no manual processes. For low volume production, only the automation or high volume production processes need to be used as far as the volume of the production is concerned. Likewise, geometry. Thin sheets you cannot cast. As I gave you example last time, thin sheets you have to, raw material is to be deformed into the desired shape, like all car bodies or the like trunks or even the aluminum products which are made of thin sheets, they are made by the deformation, and then final finishing is and dimensioning is done through the machining. That is fine. Okay, so the geometry and tolerance are the other parameters. Once if you have done this, then identify from that list, identify the suitable potential processes, and from this list, based by putting in these two, you can now put in you can choose like which process out of those say few processes left, you select based on your experience, based on your exposure, which process will be giving you the minimum cost, which will be giving you the desired production rate, okay, which will be giving you the desired quality of product. So again you choose the fewer processes based on your experience. So this will be coming down again, say from 10, you earlier you had 100, now you reduce 10, now 10 out of 10, say you have reduced again to 4. Out of 4, 1 has to be chosen. So now we can come up with a decision matrix. Okay, the decision matrix works in very simple way, like this. Okay, so here we will be writing the parameters which are being considered. Say the low cost is important, the production rate is important, the quality of the product that is being realized is important, and the flexibility, say, another aspect. Okay, it is possible that all these parameters may not have the equal weightage. Say you want to give maximum weightage to the cost, then highest weightage is given to the weight, to the particular factor is to be given, say. So if the cost is most important, give the maximum weightage to the cost. If the production rate is important, give the maximum weight to the production rate. So say, or if it is the quality is important, give the weight to the quality, which can be realized to the option 1, which may be from casting, forming, machining, or welding. Say particular, there will be a specific category of the processes in these broad group of the processes. Okay, so if the cost is of the greatest importance, you want to manufacture, thereafter cost, the quality is important, so give the weightage 15, say, for cost, for 12 for quality, production rate is 10, and flexibility, say, 8. If these are the different, you can assign any weight as per your convenience, as per your the relative importance among these factors. Now all these options of the available processes now need to be rated in a scale 1 to 10 or maybe 10 to 100. It's your choice. Okay, now you give the rating, all right, as per your the choice, and then rate the processes, process 1 in terms of cost. Say if it is being rated in 1 to 10 scale, then say 6. In terms of production rate, it is rated 8. In terms of quality, it is rated 7. In terms of flexibility, it is rated low, say 4. Okay, likewise the different processes can be rated for different processes can be rated in terms of cost, production rate, quality, and this. Okay, I'll give another example. Like say cost wise is very good, say forming 8, so it is very good, 8, and if it is production rate wise it is also good, so you may give say 10. If it is quality wise it is low, so you may rate 5. Quality wise, say it is less flexible, so you may rate 4. So now what you have to do is multiply the weight factor with these values. So here you will have 90, here you will have 80, here you will have 84, and here you will have 32. Obtain the sum of this value. Okay, similarly multiply the weight factor with the scale or the value assigned to the another process. So here it is say 120, right, and here it is 100, here it is 60, here it is 32. Again obtain the weight. Likewise for all food processes, sum of all these weighted factors values are identified, and one which is having the highest value, that process is chosen. Say among here, if you are getting just for an example, I don't know how much the total will be. Say here it is 320, and here it is 180, here it is 120, and say here it is coming 50. Right. So obviously the one which is having the maximum score, that will be chosen for the selection. So this is how actually the decision matrix, when you are dealing with the multiple factors, multiple options, you can apply the weighted decision matrix for choosing the suitable process. Okay, so now probably I have completed all this selection related thing. There are a few more slides, but that will be just a repetition. So here I will stop. Yes. See, yeah, I agree with the observation, and this is what is needed. If you feel the kind of the importance being given or weight being assigned is you are not satisfied with that, there is no fixed way of identifying the of giving the weightage to a particular parameter. If you agree on the weights being assigned, then let us go with that. Okay, and it is not done by one person. These kind of things are done by a group of members. Like say you have 10 people, all will be doing the brainstorming, will be identifying how much weight can be given as far as cost and this process is concerned, how much value, how particular process is to be rated with regard to quality, with regard to, because this is the subjective one. I hope you will be getting. This is the subjective one. So based on the experience, and you will be getting the people in your team from the manufacturing, from the design, from the sales, maybe from the customer. So all those stakeholders are brought together. Their inputs are used to come out with what, like how to rate a particular process with regard to the parameters which are of our importance. Okay. So if we agree once, then whatever weight is coming, we need to go with that. You can always do the iterations, that is fine, isn't it? Like in one go, if you are coming up with the one process and is still not satisfied, go for the second round. Okay? So because this kind of decisions, like choosing a particular process for manufacturing something, is not done in one go, it is not done in one sitting. Just keep on thinking and try to optimize, because these are the big decisions. These will be affecting the economy of the entire plant, okay? And a lot of survival will depend upon this, like how things should be done, okay? So it's good, like you have heard and you have understood what I try to say. Okay, that's all from my side. Let me just